he loved looking for patterns in numbers. And then the puzzle side of mathematics. He wanted to prove that these patterns would be there forever.
But as well as being the basis for fun and games in the years to come, Fermat's mathematics would have some very serious applications. One of his theorems, his little theorem, is the basis of the codes that protect our credit cards on the internet. Technology we now rely on today all comes from the scribblings of a 17th century mathematician. But the usefulness of Fermat's mathematics is nothing compared to that of our next great mathematician. And he comes not from France at all, but from its great rival. In the 17th century, Britain was emerging as a world power. Its expansion and ambitions required new methods of measurement and computation, and that gave a great boost to mathematics. The university towns of Oxford and Cambridge were churning out mathematicians who were in great demand. And the greatest of them was Isaac Newton.
I'm here in Grantham, where Isaac Newton grew up, and they're very proud of him here. They have a wonderful statue to him. They've even got a shopping centre, the Isaac Newton Shopping Centre, with a nice Apple logo up there. There's a school where he went to, which has got a nice blue plaque, and there's a museum over here in the town hall, although actually one of the other famous residents here, Margaret Thatcher, has got as big a display as Isaac Newton. In fact, the Thatcher cups have sold out, and there's loads of Newton ones still left, so I thought I would support mathematics by buying a Newton cup.
And Newton's maths does need supporting.
Newton's obviously very famous around here. Do you know what he's famous for?
No. Discovering gravity.
Gravity?
Gravity, yes.
Gravity?
Apple tree and all that.
Yeah.
Gravity.
Gravity.
And that pretty much summed it up. If people know about Newton's work at all, it is his physics, his laws of gravity and motion, not his mathematics.
You're in a rush, okay. Acceleration, you see, one of Newton's laws.
"8 miles south of Grantham, in the village of Woolsthorpe, where Newton was born, I met up with someone who does share my passion for his mathematics.
This is the house.
Oh wow, beautiful.
Jackie Steddle is a Newton fan, and more than willing to show me around the house where Newton was brought up.
So here is the, well, you might call it the dining room. I'm sure they didn't call that, but the
Right,
room where
yeah.
they ate, next to the kitchen, and of course there would have been a huge fire in there.
Yes, gosh, I wish it was there now.
His father was an illiterate farmer, but he died shortly before Newton was born. Otherwise, the young Isaac's fate might have been very different.
And here's his room,
Oh, lovely, wow.
as we think.
Oh, they preserved
So-
it really nicely. It's got
Yes.
a real feel of going back in time.
It does, yes.
I can see he's as scruffy as I am. Look at the state of that bed. That's how I think I left my bed this morning.
Newton hated his stepfather, but it was this man who ensured he became a mathematician rather than a sheep farmer.
I don't think he was particularly remarkable as a child.
Okay, so there's hope for all those kids out
Yes,
there.
yes. I think he had a sort of average school report. He had very few close friends. I don't feel he's someone I particularly would have wanted to meet. But I do love his mathematics. It's wonderful.
Newton came back to Lincolnshire from Cambridge during the Great Plague of 1665, when he was just 22 years old. In 2 miraculous years here, he developed a new theory of light, discovered gravitation, and scribbled out a revolutionary approach to maths, the calculus. It works like this.
I'm going to accelerate this car from 0 to 60 as quickly as I can. Now, the speedometer is showing me that the speed's changing all the time, but this is only an average speed. How can I tell precisely what my speed is at any particular instant? Well, here's how.
As the car races along the road, we can draw a graph above the road, where the height above each point on the road records how long it took the car to get to that point. I can calculate the average speed between 2 points A and B on my journey by recording the distance travelled and dividing by the time it took to get between these 2 points. But what about the precise speed at the first point A? If I move point B closer and closer to the first point, I take a smaller and smaller window of time, and the speed gets closer and closer to the true value. But eventually, it looks like I have to calculate 0 divided by 0. The calculus allows us to make sense of this calculation. It enables us to work out the exact speed and also the precise distance travelled at any moment in time.
I mean, it does make sense of things which we take for granted so much.
Yeah.
I mean, things that, if I drop this apple,
Its distance is changing and its speed is changing, and calculus can deal with all of that.
which is quite in contrast to the Greeks. And Greece
Yes.
is a very
It's
static
static,
geometry.
yes, and yes, it is.
And here we see.
Yeah.
So I mean, the calculus is used by every engineer, physicist,
Absolutely,
because
yes.
it can describe the moving
Yes,
world.
yes, and it's the only way really you can deal with the mathematics of motion or with change.
There's
Yes.
a lot of mathematics in this apple.
Newton's calculus enables us to really understand the changing world, the orbits of planets, the motions of fluids. Through the power of the calculus, we have a way of describing with mathematical precision the complex, ever-changing natural world. But it would take 200 years to realise its full potential. Newton himself decided not to publish, but just to circulate his thoughts among friends. His reputation, though, gradually spread. He became a professor, an MP, and then warden of the Royal Mint here in the City of London.
On his regular trips to the Royal Society from the Royal Mint, he preferred to think about theology and alchemy rather than mathematics. Developing the calculus just got crowded out by all his other interests, until he heard about a rival.
A rival who was also a member of the Royal Society, and who came up with exactly the same idea as him: Gottfried Leibniz. Every word Leibniz wrote has been preserved and catalogued in his hometown of Hanover in northern Germany. His actual manuscripts are kept under lock and key, particularly the manuscript which shows how Leibniz also discovered the miracle of calculus shortly after Newton.
What age was he when he wrote?
He was 29 years old, and that's the time, within 2 months, he developed differential calculus and integral calculus.
Really, in 2 months. So it was all fast and furious when it comes. It's yeah. There's a little scrap of paper over here. What's that one?
Yeah,
Is that a letter or?
That's a small manuscript, and Leibniz notes. Sometimes it happens that in the morning, lying in the bed, I have so many ideas that it takes the whole morning, and sometimes even longer, to note all these ideas and bring them to paper.
Right. No, I suppose that's beautiful.
I suppose that he liked to lie in the bed in the morning.
A true mathematician. Yeah. Spends his time thinking in bed. And I see you've got some paintings down here. So this is
a painting.
This is what he looked like. Right.
Yeah.
Even though he didn't become quite the 17th century celebrity that Newton did, it wasn't such a bad life. Leibniz worked for the royal family of Hanover and travelled around Europe representing their interests. This gave him plenty of time to indulge in his favourite intellectual pastimes, which were wide even for the time. He devised a plan for reunifying the Protestant and Roman Catholic churches, a proposal for France to conquer Egypt, and contributions to philosophy and logic which are still highly rated today.
He wrote all these letters. I mean, that's absolutely extraordinary.
Yeah.
He must have cloned himself. I can't believe there was just one Leibniz.
But Leibniz was not just a man of words. He was also one of the first people to invent practical calculating machines that worked on the binary system, true forerunners of the computer. 300 years later, the engineering department at Leibniz University here in Hanover have put them together following Leibniz's blueprint.
I love all the ball bearings. So these are going to be our zeros and ones. So a ball bearing is a
only
one.
zeros and one.
Yeah.
Now we represent the number 127. In binary, it means that we have the first 7 digits in 1.
Yeah.
And now I give in number 1.
Okay.
Now we add 127 plus 1
Yeah.
is 128, which is 2 power 8.
Oh, okay. So there's going to be lots of action.
Would you show this here?
So this is the money shot. So we're going to add 1. Oh, here we go. They're all carrying. So
This 128, this is 2 power 8.
excellent. So 127 in binary is 1, 1, 1, 1, 1, 1, 1, which is all the ball bearings here. To add 1, we need, it all gets carried. So this goes to 0, 0, 0, 0, and we have a power of
to 2 here. So
Right.
this mechanism gets
Yeah.
rid of all the ball bearings that you don't need. It's like pinball, mathematical pinball.
Exactly.
I love this machine.
After a hard day's work, Leibniz often came here, the famous gardens of Herrenhausen, now in the middle of Hanover, but then on the outskirts of the city.
Something about mathematics and walking. I don't know, you've been working at your desk all day, all morning, on some problem and your head's all fuzzy and you just need to come and have a walk. You let your subconscious mind kind of take over and sometimes you get your breakthrough just looking at the trees or whatever. I certainly had some of my best ideas whilst walking my local park, so I'm hoping to get a little bit of inspiration here on Leibniz's local stomping ground.
I didn't get the chance to purge my mind of mathematical challenges, because in the years since Leibniz lived here, someone has built a maze.
Well, there is a mathematical formula for getting out of a maze, which is if you put your left hand on the side of the maze and just keep it there, keep on winding round, you eventually get out. That's the theory, at least. Let's see whether it works.
Leibniz had no such distractions. Within 5 years, he'd worked out the details of the calculus, seemingly independent from Newton, although he knew about Newton's work. But unlike Newton, Leibniz was quite happy to make his work known. And so mathematicians across Europe heard about the calculus first from him and not from Newton. And that's when all the trouble started.
Throughout mathematical history, there have been lots of priority disputes and arguments. It may seem a little bit petty and schoolboyish, but we really want our name to be on that theorem. This is our one chance for a little bit of immortality, because that theorem's going to last forever. And that's why we dedicate so much time to trying to crack these things. And somehow we can't believe that somebody else has got it at the same time as us. These are our theorems, our babies, our children, and we don't want to share the credit.
Back in London, Newton certainly didn't want to share credit with Leibniz, who he thought of as a Hanoverian upstart. After years of acrimony and accusation, the Royal Society in London was asked to adjudicate between the rival claims. The Royal Society gave Newton credit for the first discovery of the calculus, and Leibniz credit for the first publication. But in their final judgment, they accused Leibniz of plagiarism. However, that might have had something to do with the fact that the report was written by their president, one Sir Isaac Newton. Leibniz was incredibly hurt. He admired Newton and never really recovered. He died in 1716. Newton lived on another 11 years and was buried in the grandeur of Westminster Abbey. Leibniz's memorial, by contrast, is here in this small church in Hanover. The irony is that it's Leibniz's mathematics which eventually triumphs, not Newton's.
I'm a big Leibniz fan. Quite often revolutions in mathematics are about producing the right language to capture a new vision, and that's what Leibniz was so good at.
Leibniz's notation, his way of writing the calculus, captured its true spirit. It's still the one we use in maths today. Newton's notation was for many mathematicians clumsy and difficult to use. And so while British mathematics loses its way a little, the story of maths switches to the very heart of Europe, Basel. In its heyday in the 18th century, the free city of Basel in Switzerland was the commercial hub of the entire Western world. Around this maelstrom of trade, there developed a tradition of learning, particularly learning which connected with commerce. And one family summed all this up.
It's kind of curious. Artists often have children who are artists. Musicians, their children are often musicians. But us mathematicians, our children don't tend to be mathematicians. I'm not sure why it is.
At least that's my view, although others dispute it. What no one disagrees with is there is one great dynasty of mathematicians, the Bernoullis. In the 18th and 19th centuries, they produced half a dozen outstanding mathematicians, any of whom we'd have been proud to have had